Alright, this is Cal 1, Applications of Differentiation, and we're going to be talking about what differentials are. And maybe, if I feel like it, we'll give a definition of differentials. Anyway, so this is just going to be an introduction to differentials, and then further on into the lesson we'll be working a lot of examples. And so what we're going to do here is I'm going to start with a picture. So we have a curve, and this curve here is defined by y is equal to x squared, and then I've got a tangent line at this point right here to the curve. And here's the whole idea of this differentials that we're going to be talking about. We need to understand the concept of the tangent line approximation. By using points on the tangent line to actually approximate a value on this curve right here. Now we're going to use we're going to look at some look at an example here. Let's say that we go out to where x is equal to 2, and as you can see my y value is 4. Now remember, this is y is equal to x squared, so 2 squared is 4. And then we pick where x is equal to 2 on the tangent line right here, and its y value corresponds to 3. Now, I don't know if I mentioned it or not, but this is the point right here, 1, 1. Well, take a look at the y values. We have 4 and 3. So if we were trying to get an approximation of the y coordinate, that's a difference of 1, and I don't think that's going to be a very good approximation. But as you see, as we get closer and closer, okay, as our, this would be our delta x here, as it gets smaller and we get closer and closer to this point here, the y values here, their difference is going to become smaller. So let's look at another one. We'll turn those off, and let's look at another one here. So this time x is 1.5, and as you can see, well, this is overlapping here, but the y value, let me so as you can see, y here is 2.25, and we have 2, and this is the point on the tangent line. So the difference between these two here is going to be 0.25. So you can see this approximation is getting better, I'd have to say, because this difference in the two y values is getting smaller. Alright, and of course we'll go ahead and now let's look at, okay, so we got the purple dot here, so we are now at 1.1. So as you can see, this is 1.1 and our y value is 1.21. Now let's look at the point on the tangent line, which you can't really tell because it looks like they're overlapping. Alright, so this is an actual point on the tangent line here, and that's 1.2. And if I remember right, this is 1.21. So you can see this is occurring just above, right, the actual point that's on the tangent line. So you could use the tangent line as an approximation when x is equal to 1.1. I mean, look how close they are. That's pretty close, right? So that's going to be the whole idea in the differentials, and of course you could go in this direction also, I suppose, but we're going to be staying above, up here above it, and that's really it. By using the tangent line to do an approximation. Alright, so that's basically the whole concept here. All right, this is basically going to be a continuation of the introduction on differentials. So we're going to draw some pictures now. Alright, so hopefully I can draw us up a picture and we can make sense out of what it is. So by remembering what our graph looked like in the in this previous example that I had worked, I'm going to go ahead and just kind of draw part of a curve here, and we'll just draw it up something like that right there. Alright, and now I want to draw a tangent line, and we'll pick the point, let's say right here. And so now we're going to draw a tangent line. I'm going to attempt to draw a tangent line anyway. Okay, and you know what, I think I'm going to throw in an XY axis, so it kind of gives us an idea of where we're at here. So here's the Y axis, and we'll say this is the X axis here. Good enough. This point right here, which is the point of where the tangent line is occurring, and we'll call this on the x-axis the letter C. So this particular point right here, I'm going to draw it. We're going to have a bunch of stuff drawn on here. So this ordered pair right here is going to be C and F of C. Alright, so you should be able to follow that pretty easily. And remember, we talked about, I'm going to go way out here, so let's pretend we're really zoomed in on our picture. And let's talk about this, right, this difference right here. Okay, so if this difference is really small, then we could use this tangent line to approximate the y value. Instead of using the y value on this graph here, we could actually use the y value on the tangent line to approximate this the y value here. So that's kind of the idea. This distance here is going to be our delta x. So this is the change in x, the delta x between C and this point here. And so therefore this point is going to end up being C plus delta x. Okay, that'll be C plus delta x. And I think I'll use a different color here because I'm going to do some dotted lines. Kind of keep us an eye. Whoa. Right, and dotted lines coming down to here. Of course, we got a dotted line that we're going to need to talk about going across to there. And then we've got kind of some, right, this dotted line here. And also, this is going to kind of help us out with what delta y is. I'm going to go ahead and extend this out to right about here. Alright, so this distance, let me go back and change my color here. This distance from here to here is the distance f of C. Right? So this is f of C, this distance from here to here. Question is, what is this distance from here to here? Well, this is delta x right here. This distance is delta x, and then we want to find what is this distance here. Well, believe it or not, this is going to be f prime of C times delta x times delta x. That will be this distance this point, which I haven't stated what that point is, but right, that's going to be C plus delta x. This ordered pair will be, we'll write that right up here. So this is C plus delta x, and then we'll have f of C plus delta x. And of course we got to close that off. So that's going to be this point right here, the point on the curve. Now we have this distance from here to the point of where the tangent line meets the curve there, and that is delta y. I'm sure you got to be asking some questions. This is the confusing one here. You see, when delta x is small enough, f prime of c times delta x is really approximately delta y. So as you can see here, as this distance gets smaller and smaller and smaller, right, what's happening, well, this f prime of c times delta x is really approaching the delta y here. And I don't think I left, what did I leave? Did I leave anything off here? Of course, we know this distance from here to here is our fc plus our delta x. So the whole idea is if delta x is small enough, this is going to be equivalent to our delta y. Let me just write that right here. So delta y, which is actually equal to the f of c plus delta x minus f of c, and I've kind of run off the screen over here, but right, so here's my f of c here, subtracting off from the f of c plus delta x, you get this difference right here. But when the delta x gets, right, when the delta x, as the delta x decreases, okay, this whole thing right here is approaching the delta y, and therefore we could say that this delta y, this is approximately f prime of c of delta x. All right. And of course we're going to work some problems here, but this is just kind of the picture in a nutshell. Hopefully you've made some kind of sense out of this thing. I think maybe now I'm going to work a problem first, and then we'll talk about the actual definition of differentials. How about we do that? Alright, so we are working differentials, and this time we're going to compare delta y and dy. So we're going to compare both those values, and we're going to be working out a problem. But first, before I read this problem, actually, let's go down to here. I heard a strange noise, and I don't know where that came from. Anyway, that was weird. Okay, so when we're talking about our function, it needs to be differentiable on an open interval that's containing x, of course, and our dx, or our x, can be a non-zero real number. Alright, anyway, and we're stating some definitions here. The differential of x is denoted by dx, and the differential of y is denoted by dy. Alright, and dy is actually, what is that? That's telling me that somebody's on this page. I don't know how that's possible. Anyway, dy is equal to f prime of x dx. So of course you've seen this as dy over dx is equal to f prime of x. So basically what we've done is just taken the dx over to the right. Alright, let's get up here. We're going to let y equal x squared. We're going to find dy when x is equal to 1. And dx is equal to 0.01. So I want you to think back at that very first picture that I showed in this lesson about, you know, the closer we get, or the smaller dx gets, the better the approximation becomes. We're going to compare this value with the delta y for x equals 1. Alright? And the delta x is equal to 0.01. Okay. So I guess we need to bring up the board and get started. Alright, so our y is, got a couple things to do here. Okay, so y, remember, was equal to x squared. And we want to find dy when x is equal to 1. So the first thing I'm going to do here is I'm going to go ahead and take the derivative of this thing. That's what I'm going to do. So we've got y prime is equal to 2x. And sometimes you're going to see, you'll see them like convert this over like f prime of x is equal to 2x. Maybe I should just write it like that. Remember that y is equal to f of x, which is equal to x squared. I don't know, you know, why I'm doing this, but anyway, and then so f prime of x is equal to 2x. Right, so we're taking the derivative. Remember, this is going to be the slope of that tangent line. And therefore the differential of dy is given by, so here's dy, and that's going to be equal to f prime of x dx. F prime of x dx. Okay, and remember, this is when x is equal to 1. Okay, so we don't forget that. We're going to end up having, go ahead and plug the values in here. We've got f prime of 1 times, and then our dx is going to be 0.01. Okay, that's our dx right here. And I'll just continue to write dy. So we plug this in and we end up getting 2 here times 0.01, and that's going to end up being equal to 0.02. And remember that this is the differential of y here. This is the differential of y. So this is our dy. 0.02. What about now finding our delta y? So delta y was equal to f of x plus delta x minus f of x. Right, so that's what our delta y was. So all we have to do is just plug in our numbers. So delta y is equal to, so this ends up becoming 1.01, f of 1.01. Right, we are at 1 and we're adding the delta x, which is the 0.01, minus the f of 1. And of course, when you do the math on this, right, so we're just plugging this into the function here, 1.01 squared. Well, I guess I won't skip any steps on that. 1.01 squared minus 1. And this is all going to end up equaling 0.0201. So this is pretty close, I'd have to say, to our dy. That's pretty close to our dy. And of course, the smaller dx gets, the closer these two numbers are going to become here. All right. So really what we could say is that our tangent line, which happens to be, I didn't construct the actual equation to the tangent line, 2x minus 1, is a good linear approximation or tangent line approximation to the graph of f of x is equal to x squared at x equals 1. Alright. So hopefully you were able to follow some of this stuff. But all you got to do is go back to the very first picture that I drew and or had it graphed and get an understanding of what's going on. So I guess I'll work another application problem. Well, we're working some Cal 1 problems. I call it Cal 1. It's usually first semester of calculus. We sometimes call it Calculus 1. So anyway, whatever. We're doing differentials, and here's problems we're going to be working on. We're going to do estimation of error concept. We're going to be given a ball bearing measured to be 0.9 inches. I guess I should have put 0 in front of that. I don't know. Alright, 0.9 inches. If the measurement is correct with 0.01 inches, we're going to estimate the propagation error in the volume V of the ball bearing. Okay, so and something else we're going to do, we're also going to find relative error and percent error while we're at it. All right. So it's not going to be too bad. You're going to need to know a formula, and that's the formula for the volume of a sphere. The volume of a sphere. Okay. Alright, the first thing I'm going to do here is maybe let's state a formula we're going to need. The volume of a sphere is V is equal to 4/3 pi r cubed, if I remember right. 4/3 pi r cubed, and then state some numbers that we talked about, and that is the radius of the ball bearing is to be measured at 0.9, I think said inches or something like that. 0.9 inches, and our measurement is to be correct within 0.01, so that's going to be our delta R. Our delta R will be stated as 0.01, and actually it's going to be like within 0.01, so that means it's going to be a plus 0.01 and a minus 0.01, so a minus 0.01. So we got to be within that tolerance there. Now, to approximate the propagated error in the volume, we want to differentiate V to obtain dV over dr. So you should know how to do this. So we got dV over dr, right? We're taking the derivative of the volume with respect to r. So we take the 3, bring it out front. So we're going to be left with 4 pi r squared. 4 pi r squared. Now, to approximate delta V by dV, remember that's what we're wanting to do. that approximation thing. So d delta V, which is going to be approximately dV. Right, and remember what dV is. Okay, we're going to take the dr and bring it up to the top, but this is going to be equal to 4 pi r squared dr. Alright, 4 pi r squared dr. And now what we're going to do is simply just plug our numbers in. We've got, we just plug our r in and then our dr. Remember the dr up here? So let's just do that. So we have 4 pi, and then this is 0.9 squared. Now remember dr, right, is our delta r. I think I mentioned that somewhere in there. And that's going to be the 0.01. 0.01. Now remember, this is plus or minus here. Okay, we don't want to forget that. And of course, we plug all this into the calculator and we end up. So I plug this into the calculator. I don't think I can do this in my head, but now remember, this is plus or minus here. All right. So we did a 4 times pi times the 0.9 squared times the 0.01, and I'm getting plus or minus, and we're going to go out, let's see, a few decimal places, 0.1017, I don't know, 9. How about we go out to there? And of course we don't want to leave off our units. We were in inches, so this is going to end up being inches cubed, or cubic inches, just because, remember, we're talking about volume here. So this is plus or minus. And this actually is an approximation sign, so we can bring that delta V right on down through here. Okay. So the propagated error of this volume, this is considered to be the propagated error. You can round it to decimal places if you want. Is going to be the 0.10. Okay, so this is considered cubic inches. That it would be considered your propagated error. Now let's talk about how to get the relative error and the percent error, which is pretty easy to do. Pretty darn easy to do. Okay, so this is going to end up being the relative error, and what we're going to do is we're just going to take dV over V. dV over V, so this is 4 pi r squared dr. 4 pi r squared dr over the volume, and the volume, of course, is 4/3 pi r cubed, right? 4/3 pi r cubed, and then we want to simplify this thing down, and we end up getting 3 dr over r. 3 dr over r. 3dr over r, and then from there we just plug in our numbers. So 3 times, now remember what our dr was. It was the plus or minus. I'm going to go ahead and write it in here. This was a 0.01, and this is over our 0.9. Alright, so this is going to end up being our relative error once we do the calculations on that. And then the percent error is you're just going to move the decimal place. Move the decimal place 2 places over to the right and throw a percent sign on the end. So that's basically it. So this is the relative error here. Of course, you want to finish this up on the calculations. I guess I'll do that. Alright, so I've got out the calculator there, and this becomes plus or minus 0.033. I don't know, we'll end another 3 right here. Alright, and that of course is your relative error. Okay, that's your relative error. We'll do that, relative error. And then your percent error, you just move it over 3 places, so 3.33%, and that is going to end up being your percent error, and of course it'll be a positive there.